Alright, so today we're working through the solutions to the electric field practice problems. At this point you should have already done these problems, but if you want to look at the solutions to any one of these 6 problems that I gave you, you'll be able to find the solutions here, so feel free to jump ahead to whichever problem you want to review. So we'll start with number 1, where we're checking to make sure that you know the direction of the electric field, or broadly the electric field lines around positive and negative charges. So for a positive charge, if I'm looking for the electric field, the direction of the electric field, again, this is the direction that the force would point if I put a small, basically 0 positive test charge in the vicinity of the charge. So I put a small positive test charge in this area, and then I should be able to see that the force is going to point away from my positive large source charge that I start with. All right, and so this is indicating the direction of both the electric field vector. So if I get rid of this charge altogether and I say what's the electric field at this point P, all right, the electric field is going to point away from the positive charge. So I can write this again just with the electric field lines, which will all be pointing away from my positive charge. And then the exact opposite will be true for the negative charge. All right, so if I have a negative charge that I'm starting with, I put my tiny 0 positive test charge in the vicinity. That force will point towards the negative charge, but then if I get rid of that charge and I say what's the electric field at this point P, I'm going to be able to say that that electric field vector will point towards the negative charge, or again, the electric field lines are all going to end on this negative charge. All right, so it's pointing towards the negative charge. All right, so part of what that tells me is that the answer for this problem is going to be B. Right, the electric field lines point away from positive charges and towards negative charges. The other thing that I'll remind you of is that this is not part of the magnitude. All right, so the magnitude of the electric field is given by the following equation for point charges. Right, where I've got KQ1, the magnitude or absolute value of Q1 divided by the distance squared, right, where that distance is how far the charge is from whatever point we're looking at. And this is just going to tell me the magnitude, and I need to be looking at whether the charges are positive or negative to tell me something about the direction. All right, looking at the second problem. All right, we're looking at a free electron and a free proton that are placed in identical electric fields, all right, or an identical electric field. So one way that we can imagine this is that I've got a situation where I've just got a constant electric field. In this case, I've got a constant electric field that's pointing to the right. And I want to compare the electric force on each particle and how the accelerations of those particles compare. All right, first of all, I'll note that when I say a free electron or a free proton, I mean that these particles, these charges, are free to move. And so we're just looking at what direction they're going to be moving and how quickly they'll be speeding up. All right, so one way that we can do this is by looking at the equation relating the force to the electric field, right? And that is that the electric force is equal to the charge times the electric field. Right, so the electric field is going to be constant in both of these cases, so then the only difference is going to be the charge. All right, so Q for the proton is going to be a positive E, or a positive 1.6 times 10 to the minus 19th coulombs, and the charge for the electron is going to be a negative E, or a negative 1.6 times 10 to the negative 19 coulombs. All right, so E is this fundamental charge, it's base charge that all other charges are created from. And the only difference between the proton and the electron is that the proton is positive and the electron is negative. All right, so the electric field is the same magnitude, the charges are the same magnitude, except that one is going to be positive and one's negative. And so we can draw that on here as well. All right, so the force on the proton is going to be directed to the right, in the same direction that the electric field is pointing, and the charge for the force for the electron is going to be pointing to the left, the opposite direction that the electric field is pointing. So in comparing these electric forces, I would say that they are equal in magnitude and opposite in direction. And then the acceleration, I can get a comparison of the acceleration using that the acceleration is equal to the force over the mass. This is just Newton's second law of F equals ma, or the force equals mass times acceleration, rearranged. And so then we need to know something about the masses of the protons and electrons. So the mass of a proton is going to be 1.6 times 10 to the negative 27th kilograms, and the mass of the electron is going to be 9.11 times 10 to the negative 31st kilograms. And so more broadly, what we can say is that the mass of the proton is going to be greater than the mass of the electron. All right, so the larger the mass that I'm putting in this relationship for the acceleration, the smaller the acceleration is going to be. Right? That's an inversely proportional relationship, and so that tells me that the acceleration of the proton is going to be less than the acceleration of the electron, again because the force on the proton and the electron are going to be the same as we saw in the first part of this question. All right, for the third question, we've got these 3-point charges as shown in the figure, and which arrow, A, B, C, D, or E, is going to best represent the direction of the electric field vector at the position of the dot. All right, so one of the first ways that we can start to analyze this problem is just by creating this free body diagram analog where we're looking at the direction of the electric fields from these three charges. So first I'll look at the -1 nanocoulomb charge, and that's going to create a electric field that's going to point towards, or to the left, towards that -1 nanocoulomb charge, right, because it is negative. So my electric field for the -1 charge is going to be pointing to the left. The +3 nanocoulomb charge is going to create an electric field that's going to be going up at this 45-degree angle. And again, it's pointing away from that 3 nanocoulomb charge because it's a positive charge, so I'll call that E3 for 3 nanocoulombs. And then last, I've got the -12 nanocoulombs, which is going to create an electric field that's going towards the charge, and I'll call that the electric field 12 for 12 nanocoulombs. It's going towards it. So to really get a good sense of what direction this electric field is going to be directed, it would be useful to have some information about the relative size of the electric field on the 3 nanocoulomb charge, so E3, and the electric field from the 12 nanocoulomb charge, so E12. All right, so the magnitude for E3 is going to be K times the 3 nanocoulombs over whatever this distance, and we'll just call it R, squared is. So the distance R is going to be that center to center distance between those two, the point and the 3 nanocoulomb charges. All right, for the 12 nanocoulomb charge, I'm going to have K times my 12 nanocoulombs. And again, this is the magnitude, so I'm not going to include that negative sign. And this is a distance of 2r away. All right, so in the denominator, instead of r, I'm going to be putting 2r, right, because that's my distance. And note that it's the entirety of the 2r that's being squared. So when I simplify this a little bit more, I'm going to get that in the denominator, I've got 4r squared. And if I simplify this, I'm going to have K times 3 nanocoulombs over r squared. So comparing these two, this is telling me that the magnitude from the 3 nanocoulomb charge is equal to the magnitude of the 12 nanocoulomb charge, but they're pointing in opposite directions. So these two forces are actually going to cancel out with one another. And so all that's going to be left is this electric field from my 1 nanocoulomb charge, which is pointing to the left. So the correct answer for this question is A. All right, number 4. Each part of the figure shows 2 points near 2 charges. Compare the electric field strengths E1 and E2 at these 2 points. And so we're looking to say, is the electric field from 1 greater than, equal to, or less than the electric field at point 2? All right, so we're just going to look at what these individual electric field vectors look like to try and get a comparison. So I'm going to start with A up at the top left here and start with point 1. All right, so I've got 2 positive charges, so they're both going to be creating electric fields that are pointing away. So from this left charge at point 1, I'm going to have an electric field that's pointing away. And at point 1 from this right charge, I'm going to have an electric field that's pointing away. Now, the distance between the charges and point 1 are roughly equal. I've got the 1 plus sign, which is telling me that they're the same charge. As we can see later on, in E and F, we have multiple plus or minus signs to indicate a larger charge. So these 2 electric field vectors are actually going to be equal in magnitude in opposite direction. And so the electric field at 1 I would expect to be 0. At 2, on the other hand, both charges are going to be pointing away, so I'm going to have 2 different electric field vectors that are pointing to the right, which have different magnitudes because one charge is closer to point 2 than the other, but either way they're going to be adding together. And so this is telling me that the electric field at 1 is less than the electric field at 2. All right, for B, I'm going through a similar process. The points and charges are in the same location, except now I've swapped that right charge for a negative charge instead of positive. So again, the positive charge is going to be pointing away, so it's going to be pointing to the right. The negative charge is going to be pointing towards, so it's also going to be pointing to the right. So instead of canceling out, I'm now doubling the electric field from either of those 2 charges individually. And then looking at point 2, I'm going to have a positive charge which is pointing away. It should be pretty small because it's farther. And then the negative charge which is pointing towards. All right, so it'll be a little bit larger and pointing to the left. But these 2 electric fields are going to be partially canceling each other out, where at point 1 we're seeing that it's doubling. All right, so I'm going to say that I'm going to expect that the electric field at 1 is going to be greater than the electric field at 2. All right, for C, I've got the charges in the center, and I'm looking at what's happening outside. All right, so positive charge is going to create an electric field that points away, and the negative charge is going to create a electric field that's going to be pointing towards it, but it's going to be a little bit smaller because it's farther away. And then for point 2, the positive charge is going to be creating an electric field that points away, and the negative charge is going to be creating an electric field that points towards it. Again, the negative charge creating an electric field that's a little bit larger because it's closer. So we have larger electric fields in both cases pointing to the right, smaller pointing to the left. But if the distances between 1 and my positive charge and 2 and my negative charge are the same, then I would actually expect that these 2 vectors would cancel out to be the same. And so the diagram is suggesting that, and we'll take that suggestion. And so the answer for this one is that the electric field at 1, the strength is equal to the electric field at point 2. All right, for D at point 1, this is actually going to be the same situation as we saw with point 1 in part A. All right, so each charge is going to create an electric field that's pointing away from it, but it's equidistant in the same amount of charge, so I'd actually expect these 2 vectors to cancel out. At point 2, on the other hand, I'm going to have the vectors going at a bit of an angle, and so we would expect the x direction still to cancel out because it's on that segment that's it's going through the bisector of the line that's connecting the line segment that's connecting these 2 charges. But the y direction is going to add together, and so I would say that E1 is going to be less than E2 again, E1 in this case I would expect to be 0. All right, in part E, number E, we've got one in between the two charges again, except now that the positive charge on the right is going to be quite a bit larger, or at least 3 times as large. So I'm going to expect there to be a electric field that's 3 times as large pointing away, and then pointing away on the other one from the other single positive charge, another vector. So it's going to partially cancel out pointing to the left. But then at point 2, right, they're both pointing away. The magnitude of the electric field from the larger charge, the right charge, is still going to be the same, but then I'm going to add a little bit from that single left positive charge, and so E1 is going to be less than E2 in magnitude. And then last, we're looking at the same situation, except we've swapped the 3 positive charges for 3 negative charges. So I'm going to have a little bit pointing from the positive charge, and then a lot from the negative charge at point 1, so those two are adding together, and then at point 2, I'm going to have a lot from the negative charge pointing to the left, and then a little bit from the positive charge pointing to the right, which is going to cancel out, and so E1 will be greater than E2. All right, number 5, I've got a 10 nanocoulomb charge that's located at the origin. So I'm giving this by my big Q. And I'm looking for the strength of the electric field at the positions 5 centimeters and 0. So 5 centimeters in the x direction, 0. So I've marked that with a capital A, point A for part A. At B, negative 5, 5, so in the second quadrant. And then C, point C, in the third quadrant at negative 5 centimeters. All right, so let's start with A. So the electric field for part A, or at point A, is actually pretty straightforward, because the distance from the origin where my charge is to the point is just that 5 centimeters for the location of point A. All right, so RA is that 5 centimeters, or the 0.05 meters. If we're converting these, I'll convert the large charge down as well, make sure that we're putting those in coulombs and meters. All right, and so I can use my equation for the electric field, so K Q over R A squared, to get my value for the electric field at A. I got a value of 35,960 newtons per coulomb, or if this is, since this is technically one significant figure, bane of my existence, I will call that 40,000 newtons per coulomb. All right, for parts B and C, it's a little bit trickier because we aren't given the distance from the origin to either of those points right off the bat, but we can find them. All right, so RB, the distance for B, is going to be the hypotenuse of this triangle, where the two sides of the triangle are 5 centimeters and 5 centimeters. All right, and so I can just use the Pythagorean theorem to find the hypotenuse given the legs, 0.05 squared plus 0.05 squared. And then I can use my definition for the electric field, so K Q over RB squared, and that's going to get me a value of 17,980 newtons per coulomb, or again, in the one significant figure situation that I have done to myself, 20,000 newtons per coulomb. Now, despite the fact that point C is in a different quadrant, so the electric field's going to be pointing in a different direction, finding the distance, so I guess RC, is going to end up being the same, right? Because when I square it, the negative signs don't matter, so it's negative 5 squared plus negative 5 squared, but I'm still going to end up with the same value. So this RB is going to be the same as RC, and so if I did this all over again, right, I would get the same value, and so I would end up seeing that the electric field at point C would be the same in magnitude as point B. We can also talk just a little bit about the direction of the electric field at each of these points. Right, we've got a positive charge at the origin, and so that's telling me that the electric field is pointing away from that charge. All right, so I can add in the electric field vectors at each of these points, and I'll do my best to make it so that the magnitude of the vector at B and C are equal and about half of the magnitude at A, which is what we found in our calculations. Okay, and last but not least, all right, we've got a charge Q1, that's 5 microcoulombs at the origin. Right, so my positive charge at the origin, and then a second charge Q2, which is a negative 3.00 microcoulombs, and that's on the x-axis at 0.8 meters. So I've got that as x1, 0.800 meters. And then we're looking for the electric field at a point on the y-axis, which is half a meter from the origin, and so I've marked that as a y1 in my knowns, and I've also marked point P, the location that we're looking for the electric field on my XY coordinate system that I've created. All right, so this is an electric field problem in 2 dimensions. So the first thing that I will want to do is be drawing the electric fields for each of these charges individually on my free body diagram analog. All right, so first the positive charge is going to create an electric field that's pointing away. So this is the electric field from Q1. And then Q2 is going to be creating an electric field that's pointing towards it. So here's my electric field from point 2. Right, and I can add in my coordinate system so I can define positive and negative numbers that'll be indicating my direction. All right, so I've got E2, or the electric field from charge 2, which is pointing in 2 different directions. So I will want to know something about that angle. All right, and so to do that, I can add in this hypotenuse on my diagram here, and this will be the distance. I'll call this R2P, right? Distance from Q2 to the point P. But in this, I can find this angle here, theta. Right? To do that, I can use my inverse trig functions. In this case, I already know that x1, the values for x1 and y1, so I can use an inverse tangent of x1 over y1, opposite over adjacent, to get that angle. All right, so that angle is going to show up in this diagram here, right, between the y-axis and my vector, which is right here, right, pointing on that straight line path between point P and Q2. So let's start with looking for the net electric field in the x direction, which will be the sum of the electric fields in the x direction. And in this case, I only have a component of the electric field from Q2, and that'll be the sine component to get the x direction. And so I can write out that magnitude. And I said magnitude, but we actually are looking at a vector, so I'm going to add in that negative sign, right? Excuse me. All of that's so wrong. So wrong. It's definitely positive. Definitely positive. All right, positive because it is pointing to the right as indicated by my coordinate system. All right, so that's the only force in the x direction, so we've got that x component, except that we do not have this distance r2p yet, so let's write that down. Right, again, this is the hypotenuse of my right triangle, where the legs of my right triangle are x1 and y1, so x1 squared plus y1 squared. Take the square root, and that'll give me that hypotenuse, that distance between point P and Q2. Okay. Net electric field in the y direction will have parts from both Q1 and Q2, but we're still just going to be summing the electric fields in the y direction. So I've got a positive electric field from E1 and a negative component of the electric field from Q2. That'll be the cosine of theta to get that. The cosine of theta to get that y component. So I can fill this in a little bit more detail. And this will give me the size of my electric field in the y direction. Right, again, usually I would say hold off on doing any calculations until you get to the end, but it is useful to get a sense of what direction this net electric field will be pointing. So for the x direction, I ended up getting a value of 25,697.2 newtons per coulomb, and then in the y direction I got a Alright, and so that's telling me that I've got a net force that's pointing in the x direction and in the negative y direction. And again, I can find the magnitude by using that head-to-tail summation, so I can be shifting my net force in the y direction over so that the tail of my vector in the y direction begins at the head of the vector in the x direction, and so that means that my net electric field is going to go from the tail of the x direction to the head of the y direction. Alright, so this is a right triangle, so I can find the magnitude of that right triangle using the Pythagorean theorem, and I can find my angle phi for my direction using the inverse tangent. So I'll write that out one more time. Alright, and so for our final answers for this problem, I have a net electric field of 2. One thing that I will point out is that the question is asking for the electric field at a point on the y-axis. Now, while it doesn't specify that we need both the magnitude and the direction, since it didn't specify the magnitude or the strength of the electric field, we should assume that we're just looking for the whole thing, right? And because the electric field is a vector, that means that we have to include both a magnitude and a direction. And since it's in 2 dimensions, right, the way that we indicate directions is using an angle. All right, let me know if there are any questions with any of this, and good luck.